Hey everyone, my name is Tovio, and we're going to get into a study hall here. And yeah, so I'm pretty much set up here. I've got VS Code up here, got a terminal down here, and I've got some Learn stuff over here. If you don't have familiarity with what Learn is, that's the learning platform here at Galvanize, and it's a bunch of lessons. So the format of this, I'm going to take questions from people in our Slack channel. You can get to our Slack channel by signing up for the basic prep, which is free. And there's information in the description concerning that. I'm going to take questions from the Slack channel, and maybe I'll handle a question and I'll go through a lesson on Learn, take another question, do another lesson on Learn, and kind of cycle through like that. So I'm going to take a question. Challenge 3 in the copy dictionary. Let's see if I can track that down. And in general, there's a link. Yeah, and in general, when you have a question about a specific challenge, if you could include a link to it, that's really helpful for me. So copy a dictionary, and we're looking at challenge 3. Use the code block below to do the following steps. Use the assignment operator to make a copy of the person1 dictionary below in a variable called person2. Add a key called job status to the person2 dictionary. Got a little typo there. And set its value be true to true. Use the copy method to make a copy of the person1 dictionary in a variable called person3. Delete the job status key from the person3 dictionary. Okay, yeah, so I'm just going to copy the starter code here. So person1, and so we've got this dictionary, and the first thing, use the assignment operator to, I'll just copy all these and do that, and I'll comment them all out. If you want to comment out a bunch of stuff. If you're on a Mac, it's Command/. If you're on a PC or Linux machine, it's Control/. And it's the slash under the question mark. Okay, so, you know what? Looks like my mic is a little quiet. I'm just going to turn that up really quick. Hopefully that's better. It looks like that's about right. Okay. Okay, that seems good. Okay, all right. So, yeah, if you want to, comment out or comment in blocks of text, it's Command/ or Control/ either way. Command/ on a Mac, Control/ on a PC. Okay, so use the assignment operator to make a copy of the person1 dictionary below in a variable called person2. Okay. I'm assuming we're going to use the copy method to do this. So there might be something a little bit off in the description of this. So we've got person2, and that's going to get person1.copy. Add a key called job status to the person2 dictionary and set its value to true. So person2 sub job status. That's going to be true. Use the .copy method to make a copy of the person1 dictionary in a variable called person3. I'll just grab person3, and that's going to get person1.copy again, and delete the job status key from the person3 dictionary. So let's do del person3 sub job status. Interesting. So I'm following the instructions directly here, but I think there's actually an issue with these instructions, because if I'm adding job status here for the first time to person2, which is a copy of person1. Oh, okay. Okay, I think I see what's going on here. Let's just try running this, because I think this is going to fail. But I think I know why. So let's run this. Yeah. Key error job status in person 3. So if I eliminate this .copy from person 1, notice it's not saying, it's saying to make a copy, but it's saying use the assignment operator to make a copy. And this is maybe not good language to use here. So I might go back in and correct this language, because what I'm going to figure out if we're asking, is make a variable named person2 and assign to it person1, which is not the same as making a copy of the dictionary, as it turns out. So let's see if that works. And if not, then there's an issue. Yeah, that worked. Okay, so this is bad language, unfortunately. And yeah, I'm going to grab this. I'm going to make a note to fix this. We shouldn't be saying use the assignment operator to make a copy. We should be saying use the assignment operator to assign person2, the person2 dictionary to person1. So it's not actually copying it. It's going to be the same object finally. So yeah, that's a bit confusing. Okay, cool. Here, I'll just make a note of this for myself. And this is actually a really helpful part of this process. People going through our materials, there are things that you're going to catch, things that are ambiguous, and we're going to see it and we're going to fix it. So, through you working through it and, through us presenting it at different times. Okay. This is challenge 3. Yes. Okay. All right. So let's look at another one. There's one in the Python basic strings, basic string properties section, challenge 3. Okay, let's look at that. So challenge 3. Write a function called IsNumber, which takes a string as an argument and returns the type as a string if the string is indeed a number, and the string not a number otherwise. Okay, so let's grab these. And this is not a function that's being written, it's some procedural code. And let's look at this. If the string is a number, return its type as either int or float. You will need to account for numbers with a decimal point in them. Okay, an empty string should be considered not a number. Okay, so I'm going to do this in, IsNumber. We are writing a function, sorry. I'm going to do this in a kind of, there are better ways, I don't want to say better. There are better ways to do this using built-in methods in Python, but I want to give a sort of procedural way to do this to solve it every time. And then we'll look at, we'll probably get a more Pythonic solution after that, but I just kind of want to demonstrate how you can sort of always solve a problem. Different ways where you can always solve a problem when you don't know the exact methods or functions to use. So this is called IsNumber, and it's going to take in some string, and I don't know why. Okay. So if we think about what a number has in it, and let's on the first pass assume that this is going to be a positive number. So let's make a numeric list, and this is going to have our numbers in it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's also going to have a period in string format. Oops, let me just that. And, well, yeah, let's see if we can do it with this. Let's see if we can pass the test first, assuming that these are going to be positive numbers. And I'm going to say for character in string, if character not in numeric, right? So if it's not one of those if it's not one of the characters we're seeing in numeric, actually, if why don't I do this? I'm going to make all of these strings. Otherwise, I'm going to have to do a little bit more, processing than I want to. This will just make it a little easier. So if the character is not in numeric, then let's say, then we return not a number. And then so let's say we do that. And we're going to do this in a very boneheaded way and see if it works. And then we'll make it more, we'll make it a little bit better if it doesn't, right? So this is sort of a agile approach, some kind of MVP, you know, just some minimally viable function that we're writing. So the next thing we do is, so this is going to account for anything that is, this should account for anything that doesn't contain these characters. Okay, so now we can say if dot in string return float, else, let's see if this is good enough. Else return integer, yeah, okay. Now, depending on how we wrote these tests, this may or may not work, which is fine. But let's find out. Okay, all right, so, unexpected indent. Oh, I didn't copy. Sometimes when I select everything from VS Code, it doesn't select line 1. And I've been confused about this for a long time. Oh, I see. I pasted. Yeah, okay. It did copy line 1 and just put it next to the placeholder code that was there. Okay, we failed. Float not equals not a number, and if we look at this is kind of cool. So let's solve for this error. This is kind of you know, if we're taking an incremental approach, let's solve for this, right? 9.9 point. Yeah, certainly that's not a number. So instead of saying if you know, if dot is in there, well, you know, if dot is in there, that's not necessarily an indication. If there's more than one dot, it's still not a number, right? So let's account for that. And let's say if dot in string, let's say, you know, why don't we put it here? If character not in numeric, what's a good way? Let's do this. If string.count of dot is greater than 1, return not a number. So this code is going to look a little bit clumsy, right? Because we're doing something like this. We're repeating this line. Can we use count? Yes. So we're going to use count here, and if the count of dot is greater than 1, well, then we know it's not a number. So let's see. And this is kind of an incremental approach. Sometimes we call this a test-driven approach because we're trying to just pass the tests. And if we can write code that'll pass the tests, that is sufficient for what the tests are asking, right? And often that is what we're trying to do. You know, the better the tests are, the better our code's going to be. But let's see if we can make an MVP here. Okay, we failed. And let's see. This is good. All right. So let's look at this test, this error. It's testing for an empty string. And empty string, we do not want to consider that to be a number. So, and that's right there, right? So let's get rid of it. Let's account for that. Let's say, before we do anything, let's say if the length of the string is less than 1, well, because we can't have a negative length, then let's return not a number. And at this point, actually, we could snag this and put it up here, just to save on this, right? So we don't have an extra return for not a number. So let's see if that works. The only reason I'm putting numeric here is if we consider either of these things to be a base case, well, you know what? It makes the code look a little bit not great. Let's do that. And let's find out if that works. Yeah, okay, so that worked. Now, I can come up with some instances where there is better code for this, let's say. But let's look at the solution that is suggested here, a potential solution. And let's see if that looks like what we just did. Okay, so I'm gonna just grab this. All right. Oh, this looks pretty much exactly like what I just did. I expected us to have a better, rigorous way to do this, but this is a nice procedural, easy way. You know, this is probably the way that you're going to solve it until you know better ways. When I say better, I don't actually mean they're better. Mostly I mean a certain kind of type checking where you can see if a string that contains a number-like thing in it can be converted into an int or a float. And if it can, right, then you know it's an int or a float, and otherwise it's not a number. Now that is still going to fail on one of these base cases, or let's say edge cases is how it's described here. Oh, if not string, well, that's good. We're not doing that. Let's see. Yeah, this is I kind of want to clean this up actually, because there's a little bit of redundancy in here. So I'm going to clean up the solution. I'm going to set this aside as well and clean up the solution on it, so it's a little bit better. But yeah, at the end of the day, we just look, we look for this case where the length of the string is 0, right? That's an error that we handled. The count of dots is greater than 1, because then it's not a number. And otherwise, we go through and we check every character in it against the numeric possibilities. We don't need to make this a list. We could actually just make this a string, like we see here, where it's just 0.0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in string form. That would work as well. If dot is in the string, it's a float if we've passed all of this, and otherwise it's an int. So I can't think of another edge case here that we'd have to handle, except putting in a non-string if the type of string is not a string, for instance. Yeah. Okay, so I'm actually gonna grab this and make a note for myself to come back and this is challenge, I think it's challenge 3, yeah. Okay. All right. So let's look at traversing a list, challenge 3. I'll go ahead and delete this. I think we went over this one the other day. In the code cell below, in a list called EvenNums, append all the even numbers from the original list. Iterate here. Let me do that. So we have this original list, iteration list, and there's going to be the range of numbers from 1 to 1,000 going by threes. In a list called EvenNums, append, I'll just snag this and comment it out over here so that we can do these one at a time. In a list called EvenNums, append all the even numbers from the original list, iteration list. Okay, so we're talking EvenNums. This is going to, we're going to append all the even numbers. Oh, yeah, okay, so let's just say for num in iteration list, let's say if num modulo 2 is 0, right? This is asking, is it even? Then we're going to take this EvenNums list and we're going to append to it. So EvenNums dot append the num. And the second step of this is in a variable called EvenIDX, collect all the values which are associated with the even indices in the original list. So I'm going to say for IDX num in enumerate. Actually, why don't we do this in one for loop, just to do it that way. So we've got EvenNums, and then we've got EvenIDX. Collect all the values which are associated with the even indices in the original list. So for index number in enumerate, the iteration list, we can just ask if IDX modulo 2 is 0, then we're going to not append to EvenNums, but append to EvenIDX. So that should work. I'll go ahead and run it, and actually we should print, right? So print EvenNums and print EvenIDX. Oh, Python, tell me. Oh, try this again. And so 1, 7, 13, 9, 19, these are the even indices from the original list, the iteration list, and up here, these are all even numbers, so this is the evens list. And we can see traveling by threes between 1 and 1,000, you know, these are the even numbers that we would see there. So let's go ahead and paste that back in here and see if that works how we want it to. Yep, so that worked. Accumulators parallel list challenge 3. Okay. Yeah, there's a good comment in here regarding the prior challenge that we looked at, where the person was using is alphanumeric, right? And that is a good way to go if that works for you. I tend to just hard code stuff like this into a list or into a set. You know, checking an item in a set is very fast. It's a little faster than checking in a list. So you can just make a set of the characters that would work. Or you can make a string and check in the string, or make a list, check in the list. Any of those things will work. Using alnum, is alnum, that's fine too. But honestly, I don't even do that in my own code for the most part. So maybe somebody has an argument about why that would be better. But I haven't heard that argument explicitly. I just tend to hard code those myself. Anyway, that's a reference to the prior challenge. So accumulators, parallel lists, challenge 3. Okay. Implement the function double sequence sum, which takes two lists of positive integers and computes the summation. Okay. It computes this summation, -1 to the k. So k is 1, -1 to the k times a sub k. So -1 to the, let's say, first element multiplied by a, the first element in A plus the first element in B over 1 plus the first element in A times the first element in B. Okay. I'm just going to grab this formulation and we'll commit it in code. And I'll just grab the header right here. Oh, where did that go? There it is. I'll put this down here for the moment. So generally, when we're thinking, I wonder if, so they didn't give us an example here. Why don't we just make some parallel lists just to be, so we've got A and B, and let's make 2 parallel lists. And I'm just going to populate these with numbers, and I just need to make sure they're the same length. Actually, I'm going to take this and I'm going to reverse it. Or maybe I'll just reverse it. So I'll do list of reversed of that same list. So, you know, this is, the first element in B is just going to be 9, and second element will be 8, right? And first element in A is 8, second element is 1. So now we've got those 2 lists, we can just implement this. So the first thing that we're going to think about is this, right? -1 to the k. So we can just return -1 to, oh, I'm sorry. Let's actually make an accumulator. I was sort of getting ahead of myself. Okay, so for let's do k in range the length of nums sub a. We're going to assume that both lists will be the same length, and that's fine. For k in range from notice that k starts at 1 in our summation, so that's going to be element 1, which is index 0. I'm going to leave this 0 indexed. That's my inclination. Yeah, that's my inclination, and I'm just going to stick with it. So we're going to say the accumulator is going to get -1 to the, this is actually going to be k plus 1, right? Because it's an explicit value here, k equals 1. But k for us is actually the index value, although in this summation it's represented as 1, not as 0, right? It's not the 0th element in a mathematical formulation, it's the first element. Anyway, hopefully that's not too confusing why we did that. And then we're going to do nums a sub k plus, right, and this needs to be, this is our numerator, right? Nums a sub k plus nums b sub k, and that's going to be divided by 1 plus essentially all this. So instead of adding, it's going to be 1 plus nums a sub k times nums b sub k. So now we just have to get all the parens closed properly. Actually, I think it's that. And I think we can return the accumulator at that point. So I'm going to run this just in case we're missing something. I'll just go ahead and get rid of that. Oh, yeah. Probably need to actually run it, which is print. And what is this called? Double. I'll just grab this. It's going to be A. This is going to be B. And let's find out what we get. So 0.232876, etc. So let's see if this passes our tests. There's a chance that there's something I missed in this, but I'm pretty sure that that's what it's looking for. Oh, it failed. Oh, interesting. Student results. Okay, let's look at this error. This may not be an error that helps us too much because it's just saying there's a difference between these. So student results, that's, you know, that's 0.538. This is what our function did. And it's saying that the value should be negative 0.0019. Okay, well let me see. Let me see if I did something wrong here. Okay, so -1 to the k plus 1, right? That's here. And then we've got this. A sub k plus b sub k, nums a sub k plus nums b sub k. Yeah. 1 plus nums a sub k times nums b sub k. Okay, you know what? I am not seeing an issue with this, unless there's something I'm missing. Anybody out there in the world see where this might actually be going wrong? If not, I'm gonna look at the test really quick and make sure. Just grab this and look at it behind the scenes. See what's happening. I'll just do that up here. So this is what learn looks like behind the scenes. And I'm not sure why this would give a different result now that I'm looking at it. So I'm going to grab this and try to suss this out, like what is going on exactly. So for k and then AB, and enumerate the zip of the nums a and b starting at 1, -1 to the k, plus a plus, times a plus b times a plus b over 1 plus nums a times nums b, 1 plus a times b. I mean, obviously there's something wrong with one of these. I'm just going to grab this and see if this runs. Oh, did somebody catch the error? Do you need a cum plus gets in? Oh. No. Yes. Thank you. Yep, that is definitely a problem. So let's see if this, because this is all fancy, and that's great. It's great if you can write this and understand the solution. But we don't actually need to use zip here unless we want to, right? It's great to use zip, but I'm generally going to show you solutions that, let's just find out if this works before I okay, that did work. So you don't necessarily need to perform the enumerate on the zip, etc., right? This is a way that works. This is also a way that works. And these are kind of two different approaches. They're both completely legitimate, right? This might be a little more Pythonic, but given the nature of this, I think this is more readable. You know, we're traversing nums A. We're getting the length of nums A, and that gives us the index, right? So we have the indices of K, and we can just keep using these indices. And this chunk of code, line 5, might be a little more convoluted than this very nice line right here, right? Because this gives us these variables. But at the end of the day, they're the same thing, right? And this is more an issue of preference. I think this over here is a little bit more Pythonic, but it's also a little bit ambiguous, a little more ambiguous what's happening here, right? Where you get the index, and then you get this tuple of values from A and B, which necessitates that you zip it, and of course, you enumerate to get K. You don't have to do it this way, right? You can do it in a way that is more. This is sort of a little more traditional in terms of how you would think about this in, say, another programming language. It's also very readable and easy to trace out. Either way is good, though. So, if you did take the enumerate of the zip approach, that's awesome. And it's good to know how to use all those. Cool. So I'm not seeing any other active questions. Oh, there's a question. Is it too early to ask for a detailed description of the discrete distributions, PMF and CDF, with a few examples and coding on different ways to use them? What time is it? Let's see. Let me think about that for just a second. Let's, Yeah, I might do a little bit of that. But I'm gonna hold off until toward the end of class, because it is sort of like jumping ahead in materials, and I want to get us a little bit further in where we're at in just going through the learned stuff in general, just sort of a lecturing approach. But yeah, I could give an intro to the binomial distribution, which, if you're in the premium prep class, is going to be coming up pretty soon. And it's going to look a lot like what I'll say here. Yeah, I'm going to do a little bit of work out of the learn material. And then yeah, I'll switch over to some discrete distribution stuff. Well, specifically binomial. So giving kind of a root in how to think about binomial. I'll just close these out. All right, so we left off at manipulating lists. And yeah, we've already covered some of this, but I think it's always good to kind of check in on these things. So modifying values within a list, appending to a list, and extending a list. And let's just, I'm going to do a quick scan through this, and, oh, you know what? I think we were a little further than this. No, I think this is fine. Yeah. Maybe I'll do these in another order. We'll do some copying, and then we'll go from there. Okay, so let's say we have a list, some list, And this list has values in it. It has dolphin. It has another list. Oops. Has another list with some numbers in it. It has a Boolean, another Boolean, and it has a float. Now, something to think about here is, well, what if you want a copy of this list? There's a couple ways to do that. There is a way I prefer, and that looks like this. SumList 2, right? This is going to be our copy. Maybe I'll just call it SumList copy. Is going to get SumList, and then I'm going to use this list slicing in order to gain all the items in it, right? So every item in this is going to be taken and put into SumList copy. All this is saying is I'm going from the initial element, right, to the last element, and we don't actually have to put those in there. In fact, it's a little nicer when you don't. It's a little easier to read and understand what you're doing. The other thing we could do is we could say SumList another copy, and this is just going to be SumList.copy. These two things do the same thing. They are doing the same thing, and we don't have to. You don't have to choose one over the other. One reason you might choose .copy though is that this is pretty commonly used, and it works for the other data types too. So if you have a dictionary, if you have a set, if you have a tuple, if you have any of these, then you want to use the .copy method because this indexing will not work for dictionaries or sets because those are unordered. So you can do either of these. If we want to verify that these are different objects, right, we can just look at the IDs, like the ID of SumList, and we can look at the ID of SumList.copy or SumList copy. Now, if we let's make another one and let's call it not a copy, and that's just going to get SumList. And let's look at the ID of that. So let's print the ID of not a copy. So yeah, and then SumList another copy. We're just gonna, we'll leave that where it is. It's completely okay. All right. So the ID of SumList is this 140469, etc. And the not a copy, because we only assigned it to SumList, it's actually the same object. And if we modify something in not a copy or in SumList, either way, if we modify something, it's going to change it in both. And that's just an important thing to consider. So if you want to make a copy, you need to explicitly make that copy using this slice notation or using .copy. And we can see that the object for SumList is different from the object for SumList copy. So that's copying a list. And I'll just do this, and I will get rid of these prints, and maybe these will come in handy. So modifying values within a list, pretty easy. We've already done this a number of times. SumList sub-index. Remember, these are zero indexed, so the zero indexed item is dolphin, right? So if we want to change that, SumList sub-0, this is us changing the first item in there. We can just change this to, I don't know, Ichthyosaurus? I don't know. Something like that. And if we print SumList, we're going to see that that has been changed, right? Ichthyosaurus, and then everything else is still the same. So that's, that's changing an item. If we want to append to a list, it's just the append method, and whatever item we want, this is going to put it in at the end. Another item, and if we print SumList at that point, we're going to see Ichthyosaurus, and at the end here we've got another item. Now, if we want, so we've got SumList and SumList.copy, but let's look at extending a list. So we're gonna do SumList.extend. If we want to put more than one item in here, we can do that pretty easily. So I'm gonna do 5, 6, 7, 8, and then we'll just print SumList again, like this. So I could take 5, 6, 7, 8 actually, and list to extend by, and let's just, let's grab this and declare it out here. And let's see if that extends to the list. I think it will. So yeah, so Ichthyosaurus, this chunk of numbers, blah, blah, blah. And then after another item, we've got 5, 6, 7, 8 as elements that have been added to it. Notice these are not in their own list. If you were to do append here instead of extend, then we would have appended this whole list as opposed to extending it by the contents of the list. So something to consider, we've modified SumList quite a bit, right? Let's look at the ID before, the ID of SumList, and let's look at the ID of SumList at the end. And we'll print that. It is still the same list. Even though we've modified it quite a bit, it is still the same list. And it's a collection of pointers to the objects in memory. So that list does not need to change. It's going to have the same ID. If we make a copy of it, obviously the ID is going to change. But given that it is still the same list, it still has the same reference, which we're seeing here, this 1407, etc. down here. Okay, so that's a lot of that. Let's look at unpacking a list. This is pretty straightforward, and we already talked about this on a previous day, but I'll just demonstrate it again. Let's do frog, pig, bear, and we'll do Kermit, Miss Piggy, and Fozzie. And all this is doing is taking these values. This is unpacking. It's going to take Kermit and it's going to put it into frog, Miss Piggy, put it into pig, Fozzie, put it into bear. This is called unpacking. We can do this with a lot of different data types. Anything sequential, you can do this. It's not meaningful to do this if you have a set because order is not guaranteed in a set or in a dictionary. So you do want to, consider that if you want this to be consistent, you should use a list. Sorry, you should only do it in the event of a list or a tuple. Now, this may not be obvious. Oh, let me do this. Yeah, I'll do this. I think this will be helpful to kind of get some insight. I'm going to make a function called getMuppets, and it's going to be pretty simple. Def getMuppets, and doesn't take any arguments, and we're going to return Kermit, Miss Piggy, and Fozzie, and this is going to work, right? So let's print the frog, the bear, and the pig. So we're going to print them in a different order just to verify that this is working how we'd expect. And I want you to see that unpacking, so we just talked about unpacking a list, but here we're actually unpacking a tuple. Now, the type that is returned when you return multiple objects from a function, that is a tuple. And it's list-like in that it's ordered, but it's not mutable. Tuples are not mutable. Lists, you can change the values in them without changing the ID. Tuples, you change the value. If you change the value, essentially, you are changing the tuple fundamentally, and it's going to have a different ID. It's actually going to destroy the object and rebuild the object. Here what we're seeing is we're returning these items, and they're going to unpack into frog, pig, and bear. And then when we print them, we can print them in the order frog, bear, and pig. So let's run that. And notice it says Kermit, Fozzie, Miss Piggy, just verifying that that works in that way. So unpacking is going to come up a little bit. Honestly, we don't unpack from lists very often. More often, we're unpacking from the contents returned from a function. So we talked about append, we talked about extend. Let's talk about removing items from a list. And so there are a couple ways to do this. We can, why don't we pack these into, let's put these into a list. Let's call it Muppet list. And we'll say frog, let's do bear, pig, frog. And we'll just show that this is now a list. Fozzie, Miss Piggy, Kermit. And let's do this. Let's remove let's remove Fozzie. So if I know the element, if I know what the element is, actually is, then I can just remove it like this. So Muppet list.remove Fozzie, and let's find out what that is. So now we get this result, Miss Piggy and Kermit, right? We removed Fozzie, from the Muppet list. What if we try to remove Gonzo, right? What happens there? So let's try to remove Gonzo. Notice it says value error, list.remove X not in list. So if we want to remove Gonzo, but we're not sure Gonzo's in there, we first need to check for membership. That's what this is called. If Gonzo in the Muppet list, then we can do Muppet list.remove Gonzo. But if you're not sure if an object is in a list when you're trying to remove it, just check to see if that object is in there, and before you do anything with it. So that's one way that we can remove things. What if we want to just remove the first element? Well, this will not error anymore, right? Because we're checking, and of course we're not removing Gonzo because, well, Gonzo's just not in there, right? We could put Gonzo in there. Why don't we do that? So Gonzo, we'll just add that to what Get Muppets returns. Notice now where I'm getting an error here because Get Muppets is going to return 4 items and we're only unpacking into 3. So why don't I just add, I don't remember what they decided Gonzo was. I think Gonzo was just like this mystery creature. So I'm just gonna say thing. And now we're going to remove Fozzie, and then if Gonzo's in there, we're gonna remove Gonzo. So, when we run this, we still come down to Miss Piggy and Kermit. Now, if we want to remove the second element in this list, we can do that as well. So we can do del, and this is going to be Muppet list Muppet list sub the index. And so in order to be safe with how you do this, you need to say if the len of Muppet list is greater than 1, right? Does that make sense? So if we're trying to remove the second element, which is at index 1, we need to make sure that the list is long enough to do that. If we don't do that, if we don't check for the length, then we might get an error, right? So I'll demonstrate that error in just a second. Let's run this. Notice our list just has Miss Piggy in it now. If I didn't do this, and let's say I try to remove the 4th element, right? Well, we know there's no 4th element in there. Let's see what we get. List, we get an error, index error, list assignment, index out of range. So with these things in general to write safe code, you want to check for membership if you're going to modify something that you expect to be in there, or you need to check for length, right? If the length is going to determine whether or not you can remove something at a certain index. It's just a good practice to get into. It will avoid you errors later on. So I think that's essentially it. We don't really talk about safe removal here, it looks like, but it's good to practice, safe removal. And yeah. So can I do a Muppet list.remove 0? So let's try that. Let's do Muppet list.remove, and this is going to be 0 for the first value. Let's see if that works. List.remove of x. X is not in the list. 0 is an object, right? So this is an integer that we're trying to remove. And there is no integer 0 in the list. If we want to remove the first element, the 0th element, we would do del Muppet list sub 0, right? Because this is indexing at this point. Again, this is the kind of thing. Actually, this should be greater than 2, not 1. And in this case, we would want to be safe and do make sure that there's an element in the list to remove. If the length of the Muppet list is, let's say, greater than or equal to 1, and we'll do greater than or equal to 2 in this case. And that's exactly right. Use del to remove an indexed item. Remove, use remove.remove for an item that you know is in there and you know what it is. That's the rule of thumb, exactly. So can we look at how the extend method works? Yeah, we definitely can. So at this point, if I run this, there is nothing in our Muppet list. Let's say I have lesser Muppets. No, it's not. Let's do more Muppets, and let's do Big Bird. Let's do Rizzo. Oh gosh, I'm sure there are others. Oh, Animal. Let's do those. So at this point we have an empty Muppet list, and but it is still a list, right? If we want to add multiple items to it, let's say we want to add more Muppets to it, we can do that with .extend, and this is the full functionality of extend. So .extend, we want to extend the Muppet list by more Muppets. So that's all we would do. That's all we need to do. And if I print the Muppet list now, it's going to have those items, Big Bird, Rizzo, and Animal. All extend is going to do is it's going to take the elements of a list, of whatever list you're extending by, which here it's more Muppets, and it's going to put it into another list starting at the next available index, right? So I'm going to not get rid of any of these other Muppets, so that at this point we should have Kermit, Miss Piggy, Fozzie, and Gonzo in there. And after we extend, we should have Big Bird, Rizzo, and Animal in there as well. So let's see if that works. Fozzie, Miss Piggy, Kermit, Gonzo, Big Bird, Rizzo, Animal. Does that help clear up what is happening with extend? If we wanted to add them one at a time, we would use append. And I'll just demonstrate, if you don't remember how to do extend, I'll just show you how to use append to do the same thing extend would do. So let's say for element, let's say for Muppet in more Muppets. So instead of extending, we're going to append to the Muppet list dot append each Muppet. Okay. So this functionality on lines 26 and 27, this is the same as the extend functionality. It's going to do the same thing. And so if you don't remember extend, that's not really a problem because you can do the same thing that extend does using append. And that's in general, this is a sort of true thing about Python. There's a core of the language that you need to know how to use, that with that core you can accomplish basically everything that these other special functions can do, right? And that may not be totally obvious. I mean, it may not be totally obvious when we're using all these different methods, but extend is almost superfluous, right? We don't really need it if we can write code using append that does the same thing. It's just this is 2 lines of code as opposed to extend, which is like a single method, which is kind of nice. And oh yeah, that's a great question. So I'm just gonna paste that in, and I'll just do it down here. So these 2 things are going to accomplish the same task. If we're appending the element. We're not appending the element in a list, right? And if we're extending, we're extending by the elements in a list. But yeah, we do have to have these in a list because the expectation is exactly list1.extend list2. That's exactly right. Okay, cool. So append adds it into the same list, and extend adds the new list to the end of the first list. That's the question. Not exactly. Append takes an element, right? And it takes this element and it puts it on the end of a list. Whereas extend takes a list and takes each element in that list and tacks them one by one onto the end of the list. Can you only use extend on lists? Yes. Yep, that's right. If you were using a set, like if you were looking at 2 sets, for example, if you want to quote unquote extend a set by another set, you would actually just do the union of those sets, and you would do set1.union set2. If you wanted to add an element, you wouldn't use append, you would do set1.add and then a single element. So there are equivalents between the data types, but they do use different methods. Lists you can append or extend. Sets, for example, you can add, and that's the you can add or perform unions. Okay. So I'm gonna delete all this Muppet stuff, and I think I'm going to, since there aren't any other active questions, I might pivot and look at some discrete distribution stuff. And this is going to be, I think this stuff is really fun. And what we'll do is we'll consider an approach to the binomial distribution. So if you're in Premium Prep, you're going to see a good amount of this in a couple days when we get into discrete distributions. So let me think about where to start. I think I want to start. Yeah, I think I'm going to start with counting in binary, and then we'll do a binary translator. So that's going to be dec to bin. That's decimal to binary. And then we'll do trying to think about how much time we have. Got about 50 minutes, so I think we can get through a lot of this, and we can take breaks, and I can answer specific challenge questions when you get to them. But I think this stuff is pretty fun. It gets into algorithmic thinking and kind of an exploratory approach. So yeah, why don't we do this? Yeah, let's do this. All right, so let's think about counting in binary. And this may not be entirely obvious offhand, but let's generate 4-bit binary, and we can do this in a kind of a really simple way. Let's do bin list bin list, and let's make this into a list. Why don't we do this? Let's make this into a dictionary instead. So bin list is going to be a dictionary, and let's say for I in range 2, and then let's do for j in range 2, and notice this nesting of loops. This is not generally this is not the best practice, but when we're brute forcing a way to understand something, feel free to do this kind of thing. It might help you gain some intuition around these things. So if we're building 4-bit binary, I can back up a little bit. That's going to look like, if we're counting in binary, we're going to go 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1. Okay, so the equivalent decimal values to these are, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In 4-bit binary, we can only represent decimal values up to 15, as it turns out. Now, one thing you want to notice here is how this pattern works. This is a very simple numeric system, and this is not really different from a decimal system. So let's think about this like decimal. So 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. This is our base 10 system, and notice what we do when we get to 9. 9 is going to roll over to 0, and we get 1, 0, 1, 1, 1, 2, oops, 1, 1, 2, 1, oops, not 112, but 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, and then 9 rolls over again to 2. And you can imagine we just keep going to this, and if we were dealing with 3 places, right, we can imagine there's a zeros place, there's a thousands place that we've just made invisible this whole time. And when we get to 099, sorry, not thousands, hundreds place, when we get to 099, then we're going to roll over to 100, right? And this is exactly like binary. The other thing to consider here about binary and in relation to decimal is we've got the ones place. So let's say we have the number 987. 7. Well, we've got 7 ones. We've got 8 tens. And we've got 9 hundreds. Oop, not 0 hundreds, but 9 hundreds. This, again, is very much like what we see with binary. So let's consider binary up here. So notice 1, every time 0, like we start at 0, we get to 1, and then we roll over and we increment the next thing to the left, right? So 0, excuse me, I'll drink some water. Okay, so we roll over the 1 becomes 0 again, and we increment the thing to the left. Since this is a base 2 system, not a base 10 system, we're not dealing with multiples of 10. We're not dealing with 1, then tens, and then hundreds. We're dealing with multiples of 2. And so let's consider 1101, and let's break it out in the same way that we do here. So 1101, well, we've got 1 ones place, we've got 0 in the 2's place, we've got 1 in the 4's place, we've got 1 in the 8's place. So we can add these up. We can say this is 1, right? 1 in the 1's place means, it's 1 times 1. 1 in the 4's place means it's 1 times 4. 1 in the 8's place is 1 times 8. So 8 plus 4 is 12, plus 1 is 13. It turns out that this 1101 is equivalent to 13 in decimal. 1101 in binary is equivalent to 13 in decimal. So that's just some logic as to how using nested for loops is actually going to give us, we're going to be counting, right? And L here, this L, is going to be the 1's place, the K is going to be the 2's, the J is going to be the 4ths, and the I is going to be the 8ths, right? So let's just go ahead and do bin list. This is actually, I should probably call this bin dictionary, but whatever. Let's call this binary, just to kind of get around any weirdness in naming. So we'll call this binary sub what? Okay. Well, let's the sub is going to be the decimal value. So we're going to start at 1 when we do this. And we're going to say binary sub counter. This is going to be a list that is I, J, K, L. Okay. And then when we do that, after we do that, we can return the binary. So what does this do for us? Is there an error? Doesn't look like it. Okay. So why don't we call this generate 4-bit binary, put it into a dictionary, and then traverse the dictionary. Okay. So generate 4-bit binary. Let's just put this in a dictionary called D, and I'm going to say for dec binary in d.items. Okay. Let's print the decimal value, and let's print the binary value. Okay. And let's see what that gets us. Oh, we're only printing one thing. What am I doing? I am never incrementing my counter. Okay, VS Code. I know you like running, but okay. Counter plus gets 1. This is just our decimal value, the decimal value counter. And I wasn't incrementing it. That's why we've got 0 as all 1s, which is definitely not true. So let's take a look at this now. We've got the decimal value, and then we've got the binary value. Decimal, binary, equivalent. Okay. Now, what if we want 5-bit binary instead? Well, to do that, we're going to have to add in another loop. And that just gets cumbersome. So if we want to generate an arbitrary length of binary, then we're going to probably end up using some sort of conversion algorithm here instead. And I'm going to go ahead and do that. So I'm going to comment this out. And why don't I start working on a decimal to binary translator. So dec to bin is often what we call this. The algorithm to this is pretty straightforward. I'm going to say def, and I'm just going to call this dec to bin. But let's talk about the algorithm first. So the way that this algorithm is going to work is we're going to take the decimal value, and we're going to perform modulus on that of 2, And if the modulus gives us a 1, then that's going to be a place value, a bit value of 1, right? And we're going to go from the rightmost binary position. So if we're considering this, our first modulus is going to get us this rightmost value. This is modulo by 2, and that's just telling us whether or not the number is even or odd. And then it's going to tell us whether or not the 2's place is a 1 or a 0. Then it's going to tell us whether or not the 4th's place is a 1 or a 0, the 8th's place. So every time we do this, every time we perform modulo, we are then going to floor divide by 2 as well. Okay, so why don't we do a translation? 0, 1, 0, 1. Let's convert this. So first thing we're going to do is 0, 1, 0. Let's do 49. Let's do 49. That's better. So the first thing we're going to do is 49 modulo 2. That's going to get us, well, it's going to get us 1, isn't it? Right? And then 49 floor divided by 2. Actually, why don't we move that over? 49 floor divided by 2 is going to equal, 2 goes into 4 2 times, 2 goes into 9 4 times, and then 4.5, right? But we drop that, so 24. Okay, and now we're going to do 24 modulo 2, which is going to get us 0, right? Not 14, but 24. And then 24 floor divided by 2 is going to get us 12. 12 modulo 2 is going to get us 0. And then we're looking at 12 floor divided by 2 is going to get us 6. 6 modulo 2 is going to get us, it's going to get us 0, right? And then 6 floor divide 2 is going to get us 3. 3 modulo 2. I think you get the idea here. 3 modulo 2 is going to get us 1. 3 floor divided by 2. And it's very possible I make, like, whenever I do this live, unfortunately, I usually make a mistake. But I don't think I've made a mistake yet. And if I have, please tell me. 3 floor divided by 2 is going to be 1, right? So 3 divided by 2 is 1.5. 3 floor divided by 2 is going to be 1. 1 modulo 2 is going to get us 1. And 1 floor divided by 2 is going to get us 0. Okay? And so when we represent this, this is going to be the value, I think this is right, 110001, right? So then we need to reverse it, 110001. So that's the algorithm. It's pretty simple, but we don't want to do this by hand. In fact, doing it by hand leads to errors, right? And there's a chance I made an error in here. If you've ever done comp org stuff, what you find when you do this kind of stuff by hand, I think it's torture a little bit. They make people learn this stuff, do it by hand. You very often make mistakes, and in the real world, you're going to let a computer do this. You're going to write the algorithm that is going to allow a computer to do this, which is what we're about to do. So why don't we write that algorithm? This is dec to bin, and we're going to convert a decimal number, and we're also going to set a number of bits that we want to work with. And by default, I'm going to give that 8 bits. So we're going to make a bin list. This is going to ultimately contain the bits that we're seeing over here that we've put out. And I'm also going to make a copy of the decimal value. I'm making a copy of it because we're going to modify it. In general, you do not want to modify a parameter, right? So we've got this name up here. We don't really want to modify that. We want to just give it dec like that. Okay, so I'm going to say for whatever in range, and I'm going to do this for the number of bits we're expecting. Keep in mind here that if we don't have enough bits to accommodate the decimal, then we're going to essentially have a binary number that is not actually representative of the decimal. Okay, so it's better in this formulation to err on the side of more bits than less bits. So for whatever in range, the number of bits. When I say this for whatever, we don't care about this value. We're not going to use this later, and that's why I put an underscore there. We're just using it because the range function is there. So I'm going to say the bit is going to get modulated. It is going to get modulo 2. And the bin list is going to get that bit. And then after that, we just floor divide by 2, which is exactly what we did up here. I want to verify if I did this correctly. Is 49 110001? Guess we'll find out in a second. And what we do at the end of this, because we're actually getting these in the reverse order, right? We get the ones placed first. We need to reverse the order of the bin list. So I'm just going to do return bin list. And this is a nice way to reverse it. This is a preferred way to reverse it. In fact, over using reversed, bin list : -1. Now, if you're iterating over something like this, it's different, right? You want to use reversed because reversed is a generator. But if we're just returning the list in a reversed form, this is better because otherwise we would have to say something like list of reversed of bin list, which is a couple extra steps we don't really need to do. We can just slice it into reverse and it'll be fine. Okay, so let's run this. Here's where I probably discover I performed bad binary arithmetic above, and I apologize in advance if that is the case. So we're checking for 49. Let's see what that gets us. 110001. 110001. So that is a good binary translator from decimal to binary. We could also translate from binary to decimal. We don't really need to do that because what we're doing here is we're actually building the foundation for understanding the binomial distribution, if that got lost along the way. The binomial distribution has the word, has bin in it, and it's binomial because there are two names, right? There are two potential outcomes, 0 or 1, for any given trial. Now, what we mean by that is when we look at a series of trials that all have equal probability, there are only two potential outcomes, either success or failure. The probability across those trials is going to be constant. So we often think about this like coin flips, heads, tails, right? That's binary. That's 0 or 1. We can think of tails as 0, heads as 1. And a series of coin flips, we might ask the question, what is the probability that out of 8 coin flips you get 4 heads, right? That's out of 8 trials, what is the probability of 4 successes? And we can think about that also in terms of binary, right? Where it's like, okay, well, what are all the different possibilities for getting 4 successes in 8 trials? We can represent this as binary, right? And once you start playing around with this, you can see that there's a lot of different ways to get 4 ones across 8 trials or 8 potential bits, right? So that's just 3 of them. And I could do this, and I could sit and rearrange these. That would be a way forward. I'm not going to do that. What I'm going to do instead is I'm going to kind of brute force this a little bit, and I'm going to count. I'm going to try to answer this question, in 8 trials, let's say in 8 coin flips, what is the probability of getting 4 heads? And notice that our probability here is 0.5, right? The probability of any given trial being a heads or tails being a heads is 0.5. So this is a convenient thing to understand through the lens of binary. I'm going to say def get binary, and bits will default this to 8. And I'm going to just say, I'm going to make a binary dictionary. I usually like using this dict constructor as opposed to using the open-close curly brace, because open-close curly brace kind of looks like a set. Every time I see it, I think set, even though it is a dictionary. I've been programming Python for a really long time, and I still confuse that in my head, so I just use the dict constructor. Most people don't. Most people would do that. I don't do that. I prefer this because I just want to understand what it is right away. Bins dictionary for decimal in the range from from 0. I don't need to actually put 0 in here, but I'll say from 0 to the 2 to the n bits, right? Because that is the largest number that we can expect. That's 8 bits that are all 1, right? 2 to the n bits. So for whatever I'm trying to say here, for decimal in range, from 0 to 2 to the n bits, I'm going to say bins d sub decimal. This is going to get dec to bin, right? This is the function we just wrote, of each decimal value, and we're considering 8 bits, right? And then we can just return the bins dictionary, the binary dictionary. Okay, so all we need to do here, well, we can just look at this. Let's see what we get. I'm going to just put this in our generic D for dictionary. Get binary, and we'll just use the default 8 because that's the question we're trying to answer. In 8 coin flips, what is the probability of getting 4 heads? So let's just do for, actually, do I have a print statement up here somewhere? Oh, I don't. Okay, for dec binary in d.items, let's print, oh, I totally do have this up here, don't I? Yeah, there it is. So for dec binary in d.items, print the decimal and the binary. And notice that this get binary, we can use an arbitrary number of bits, which we could not do with the nested for loop approach, right? We had to actually change, we would have to write different functions to get 5-bit or 8-bit or 12-bit binary. Here we don't have to do that. We can, we have the flexibility of, putting in however many bits we want. So let's run this. And this is all the options. So I'm just gonna, if we just look at a little subsample of this, let's indicate which of these have 4 ones. 1, 2, 3. Well, not that one, right? Oh gosh. Okay, not that one. This one does. 0, 1, 0, 0, 1, 0, 1, 1. That's got 4 ones. 1, 0, 0, 1, 1. That does not. 0, 1. This one does. 1, 0, 0, 1, 1, 1. This one does. 1, 0, 0, 1, 1, 1, 1. This one does not. This has 5 ones. 0, 1, 0, 1. This one does not. This only has 2 ones. This one has 3 ones. So just in a quick subsample, we found 3 that all have 4 ones in them. And so we actually have an approach here that can give us a probability of getting 4 heads, right? And that's in our binary, right? So if I want to do that, I might get the values out of get binary. And so let's do that. Instead of D gets well, you know what? I'll just do this. No, I'll do this. So I'll say binary only is going to get D dot values, right? And this is just going to be a list now. And I'm going to say I'm going to make something called 4 bits only. And this is going to be an empty list. I'm going to just do an accumulator pattern. I'm going to say for binary in binary only. You know what? I am overcomplicating this. Why don't we just use this? I'll just comment out. There we go. So I'm just going to collect the lists here. And yeah, we'll do it like that. Yep. And then I'm going to also get the... I'm going to kind of overcomplicate this just a little bit to demonstrate what I'm doing. I'm also going to get the values out of here. So all binary is going to get d.values. 4 bits only is our collector. And in here, we're going to say if binary.count of 1 is 4, then we're going to append that to 4 bits only. There we go. Dot append, and let's append the binary. Yep. All right. So we can now answer the question. We can answer this question above, right? In 8 coin flips, what is the probability of getting 4 heads? Well, this is just going to be the length. So let's print the length of 4 bits only divided by all the binary. Sorry, the length of all the binary. The length of all the binary. Let's find out what that is. 0.2734375. Okay. So this concept, this sum of the ones in binary, leads us to a binomial distribution. Okay, and we can take a further approach here, where we can. What's a good way to do this? We can transform this dictionary. And we wrote this get binary function again above, but we can go ahead and transform this a little bit and get a clearer sense of the distribution itself. So why don't we do that? Why don't we write another function, and let's call it, let's just call it binomial distribution for p equals 0.5. So this is going to be def, let's just do binomial distr, and we're going to pass in a binary dictionary, right? So that's like this D above. So I'll uncomment that. We'll use it when we test this out. So def binomial distribution of a binary dictionary. I'm going to go ahead and make a binomial dictionary, and let's default that to an empty dictionary. Okay. So for whatever and each value in that binary dictionary that we pass in, we're going to take those values. I could do this a little differently. I could just say for v in binary dict.values, but I usually do this. And if you've seen me code, you probably realized that I constantly forget this .items method. somehow. It's something I do a lot. So I don't know. Instead of using .values, I'm just going to use .items, and I'll forget it at some point again. Okay, so I'm going to say I'm going to get the sum of the ones, and that's as easy as summing what's in V, right? That's our binary list. And I'm going to say if the sum is not in the binomial dictionary, then binomial dictionary subsum, and notice sum underscore. I don't want to use this keyword. I'm using sum underscore. That's just a convention that I use. Not everyone does that. You could name it something else. You could do bin sum or something else like that. I just do sum underscore. And under all conditions, I want to increment that sum by 1. This might be confusing to some of you. I could say if the sum is not in the binomial dictionary, I could default it to 1, right? And say else that. I like this more. It's the same logic, though. It's the same thing. So I do this. You can do it a different way. And then I'll just return the binomial dictionary. And yeah, so why don't I, yeah, let's do this. We got D above. Let me just grab this. I'll just use it like this. Again, you know, just so that we can see it in context. And I'm going to say for k v in d.items, and we're going to just print these counts, okay? And that's what we're really getting out of this. I'm going to print f, and then is going to be k and v. And we're going to see the counts of the different outcomes. Oh, wait a minute. What am I doing wrong? Sum gets the sum of v. Oh, wait a minute. Not get binary. Binomial distribution. Okay. I need to get the binomial distribution of D. So D binom. I'll do that. And then there we go. And let's see what we get. So this may be a little small. I'll go ahead and snag it and look at it a little closer. This is our distribution. And we can see in the binomial sense, it is, you know, it's kind of bell curved like this, right? It's symmetrical. The mean is the most occurring item, right? This middle item, that is our expectation and occurs most. We have a range from 0 to 8 because we're dealing with 8-bit binary. And the sum of the ones across this entire thing is 70 for 4 ones. Now, why is that? You might think about it this way. There are more ways that you can arrange 4 ones in 8-bit binary than there are ways of arranging 2 ones in 8-bit binary. Because if you're arranging 2 ones, you're also arranging 6 zeros, and it's sort of like they don't shuffle as well that way. So 4 is going to be able to be arranged across 8 in many more ways than 2, in quite a few more ways, actually. So, you know, this is an approach to determining a binomial distribution. This is not using the binomial formula, and this does not work in the case where p does not equal 0.5, right? Where your probability is not a coin flip, a 50-50 chance, okay? Yeah, so that's some insight into constructing the idea of the binomial distribution through binary. And this is usually part of how I teach this, because otherwise we're just thinking in terms of some formulas, which is not wrong, but it's like part of this approach. So I'm gonna actually write the binomial PMF, and first I'm gonna find it in our materials. So if we go to Intro to Stats, we go to Discrete Probability Distributions, Binomial Distribution, I think we'll find the binomial PMF right here. So let's snag this. So there's our binomial PMF. If I'm going to write this, I have to do it in a couple steps, okay? And let's just consider this. We need a few functions here, and we don't have that much time, but I think I can get this in place pretty quickly. So let's write binomial PMF. Okay. The first thing we're going to need is factorial. And why do we need factorial? Well, we need factorial for the sake of combinations. So we have n choose k combinations that we're dealing with. All right. So where n is, let's say, the length of our binary, as we're thinking about it, and k is the number of successes that we're considering. So how many ways can k be dispersed across n, right? That's sort of how many ways can 1 be dispersed, 4 ones be dispersed across 8 bits, right? That's what we're determining there. So, we get our cardinality in our combinations from factorial. So let's write factorial first. So factorial of num. Everyone who is going to take the DSI should have this, that you should be able to write this basically as quickly as I can write it. We start with, this defaulted product to n, and then we say this defaulted product to 1, and then we take num and we multiply product by every value between 1 and num, including num, right? So that's, if we're doing factorial of 6, it's 6 times 5 times 4 times 3 times 2. We don't really have to multiply by 1 because, well, we don't. So for n in range, I'm just going to go from 2 to num. And remember, this needs to be inclusive, so I'm going to do num plus 1. And I'm going to say the product is going to be multiplied by n, so every one of those numbers. And then we can just return the product. We can test this, print the factorial of 5, which is going to be 120, which we can see there, so 120. Let me not print all of this above, and okay. Now, the next thing we need, since we've got factorial, now we just need this combinations. Combinations, if you're in the premium prep, we're going to go over permutations and combinations tonight. So I'm just going to write a combinations function, and it's going to be pretty straightforward. Let's see. Let me see if I can... I'm going to just track down a screenshot of the combinations function. Tuple, oops, that's intermediate Python, basic stats. I think it's going to be in basic probability. Permutations, combinations, perfect. Okay. So we've got permutations up here. Here's our generalized combinations formula. And we can just commit this directly into code. So for combinations, we're going to return the factorial of n, right? The factorial of n. And that's going to be divided by the factorial of n minus k. multiplied by the factorial of k. Is that right? Oh, the only thing that we want to consider here in addition to that is it's going to be an integer. It's going to be a count of combinations. And so I'm just going to go ahead and cast that to an integer. Otherwise, because of this division right here, it would be some value 0.0. And we don't need that. So, okay, that gives us our n factorial over n minus, this is saying r, but n minus k factorial multiplied by k factorial. So let's get rid of that. So we've taken care of this first part of combinations. So now, this first part of the binomial PMF. So now we can just write the binomial PMF. We can say binomial PMF of n, right? We're dealing with n. We also want the parameter k, and we want the parameter p, which is our probability. And we can, this is actually really simple. We've got combinations multiplied by the rest of this, right? So we can do combinations of n choose k, right? And when we can multiply this by p to the k, right, which is what we're seeing right here. And from there, we can say multiplied by 1 minus p, right? 1 minus p raised to the n minus k, raised to the n minus k. And that's all it is. So combinations n choose k times p to the k multiplied by 1 minus p to the n minus k. Okay. And what we can ask, well, let's just print the binomial PMF of out of 8 trials, 4 successes, the probability being 0.5. And we get none because we are not returning anything. Anytime you see that, it's because you're not returning something. So 0.2734375, and if you recall, let me scroll up a little bit. Oh my gosh, I'm going to have to scroll up too far. Let me print the result up here. Oh yeah, here it is, 0.2734375. Even with the same level of precision, right? It is the same. It's not even a near number. It's the same float number that we got using that brute force counting approach. So we could have done the binomial PMF using division across that brute force approach, but you might imagine that something is going to start being intractable if, with that sort of counting approach, if we're considering 8,000 trials and say 4,000 successes. This is 4,000 bits distributed over 8,000 length binary lists, essentially. Oh, overflow. Of course, there's overflow there. Let's see where we don't get overflow. It's still intractable. Sorry, it's still intractable because we're going to get a value that's too small. So let's see if there we go. Or that has, yeah, we're going to hit. Where are we going to hit that? We're going to hit an issue with combinations here. Actually, we would need to form an optimized function, an optimized combinations function, in order to actually tackle that. If you were in class yesterday, I kind of mentioned this, where because we're performing a sort of generic factorial here, we are not optimizing. It would be better if we could figure out a way to eliminate some of the numerator through simplification with the values in the denominator. But even still, we're going to get a big combinations out of this, right? If you can imagine, it's going to be the combinations, the factorial of 80 is already pretty big. And if we want to figure out how big we can go with this sort of hand-coded approach, we could do the factorial. Let's do the factorial of 200. Let's see if that works. That's a big number, all right? That is, look at that. You know, no one's trying to mess around with a number that big, you know? And notice we've got all these zeros. This is because we can't actually store the precision of this. At some point, we're going to get an integer overflow. Let's see when we get that. Not yet. Let's try 800. I'm not sure. Sorry. Let's see if. Okay. Yeah, that's a big number. It's a big number on which we cannot get meaningful value after a certain level of precision. At any rate, we can get something kind of close enough. You know, using, you know, up to like combinations on 80 and 40, 41 spread across, 40 successes spread across 80 trials. We can do that with this. We can't go that much higher than this. For example, we can't do 800, 400. But yeah. Are there any questions offhand? I'm gonna stick around for an extra 5 minutes because we started 5 minutes late. Then I'm gonna take a break before class. But yeah. I know that's kind of like a lot probably for some of you. There are things related to this in the technical interview lecture playlist. But you know, we don't go into combinations and binomial PMF very deeply in those. Mostly I just take the accounting approach toward the binomial process. Toward a binomial process. Yeah. That's basically what I meant to say. Yeah. If I don't see any questions come in, then I'm going to sign off, and I'll see those of you in class. And I might tack on an extra study hall tomorrow instead of streaming, depending on, you know, how class goes tonight, because we're going to be looking at some pretty intensive coding tonight, and I want to make sure that people understand it. So there might be another study hall tomorrow just tacked on. It won't be regularly in the schedule because usually I do stream on a data science topic on Thursdays, same time. Can we get the copy of this code? We'll need to review this further. Sure. What I'm going to do, I'm just going to paste this into, yeah, I'm just going to take this and I'm going to paste it into the Slack. And feel free to do with it whatever you want. I think kind of the neatest thing in here is that that fairly simple algorithm for converting decimal to binary. You know, if you want to challenge yourself, write an algorithm that converts binary to decimal, and you know, it's actually a little bit easier to understand than this one. But you know, these are the kinds of things that inform some algorithmic processes later, right? And you'll see that there are some algorithms that are more performant than others, right? And you might even look for other decimal to bin algorithms. Although this is the standard one. This is kind of what you would see in most cases. Okay, I'm going to sign off, and I will see. I'll see y'all in class, or I'll see you tomorrow if you're not in the premium prep. Yeah, and if you have questions, well, if you have questions, bring them to study hall. Yeah, post them in the channel, in the channels, and you know, your peers are likely to get to them before I do. I've got a lot on my plate in the next couple, well, really in the next week. But if I see questions that go unanswered, you know, for half an hour to somewhere between half an hour and an hour, I'll jump in there and I'll do my best to get on those. Lance is doing the same thing. Clark is doing the same thing. Remy's doing the same thing. So, you know, if we don't get to your questions in the channel, you know, within, if somebody doesn't get to them within 30 minutes, we'll do our best to address those pretty quickly. Yeah, thanks so much. Thanks for watching. And there will be a recording of this in the playlist for, yeah, there will be a recording of this in the playlist for the study halls. So yeah, have a great evening, and